Assalamualaikum warahmatullahi wabarakatuh. I bid to Prof. Dr. Wan Azlina and Dr. Mama Yusof. So we are from Group 1. Our group name is KIPS. So I would like to introduce our group members. First one is Ahmad Faiz. Second is me, Ariba Umaira. Third is Nur Izliana. Fourth is Nur Izyan. Fifth is Nur Shafika. And we have one additional members for our statistics group, which is Mahfuz.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shafika binti Muhammad Isa. My metric number is 20278. For the first part of the slide, I will talk about our case study. In this study, we are required to cook hot oil with water by using heat exchanger to achieve specified final temperature of oil. We are using shell and tube heat exchanger, which contain a large number of tubes packed in shell with the axis parallel to that of the shell. To find the final temperature, we will use effectiveness NTU method by Case and London. For the next part, I will talk about the introduction. The heat exchanger is a system used to transfer heat between two or more fluids. It is also used in both cooling and heating process. In this project, oil and water has been chosen as raw material. According to our case study, we have decided to use a shell and tube heat exchanger to find the specific final temperature of oil for both and cool. The heat transfer from oil that is at high temperature to water, one that is at lower temperature. This process will continue until the thermal equilibrium will be achieved.
Assalamualaikum warahmatullahi wabarakatuh. I am Nurul Izian binti Amran and my metric number is 200298. So I will proceed on process description. Okay, a heat exchanger is a system used to transfer heat between two or more fluids, which is used in both cooling and heating processes. So in this project, we have chosen shell and tube heat exchanger as our design, of which consists of oil and water as our fed. The main purpose of this heat exchanger is to cool down the hot oil, which initial temperature of 120 degrees Celsius, with water, which act as a cooling medium, which an initial temperature of 20 degrees Celsius. Okay, so why we are choosing water as our coolant? We are choosing water as our coolant is because water has excellent heat transfer properties and has a high specific heat of around 4,200 joule per kilogram Kelvin, low viscosity and no flash point. So the water will cool down the hot oil in a one shell pass and two tube pass. In this project, we are required to find the rate of heat transfer and the outlet temperature for the both fluid, cold and hot. The mass flow rate for the entire system of the water is 0.333 kilogram per second, while for the hot oil is 0.11052 kilogram per second. Okay, so let's continue to another section. Thank you.
Bismillahirrahmanirrahim. So now I am Ahmad Faiz bin Akmal with my metric number 200454 from Group 1. I will now present you our schematic diagram for our YouTube heat exchanger. Okay, so as you know from our case study, we plan to do a process of cooling oil using water as our cooling medium. So this is the design that we propose of YouTube heat exchanger with one shell pass and two tube pass. Okay. So there I have labeled all the components and also there are some dimensions there. So I will now start by telling you one by one all the components. So as for the number one, it is our stationary head channel. For the number two is our shell. We propose our shell to be standstill because of its many benefits. Some of its benefits is because it has the alloy and also nickel, which has a good resistance to corrosion, heat, and also fire. Okay, our shell diameter is also have been calculated using the formula ds equals to dB plus 98, which we obtained from the appendix from our references, and it is said to be in 273.10 millimeter. Okay, that is our shell. That is our shell diameter, and also shell also the place where our cooling medium water will flow. Okay, then number three. Number three is our tube. Okay, this is where our oil will flow, and we suggest that the material for our tube will be the copper because of its reliable quality and also good conductivity, so that heat can flow more efficiently. We also assume that the length of our tube is to be 2 meters. Okay. Then number 4, we have our shell set fluid in. This is where the entrance for our cooling medium water. We will enter the shell by this entrance. And then number 5, there are 2 vent connection there. The vent connection have the function to regulate air pressure in our shell. Okay. Number 6, we have our buffers. Okay, our buffers there we use the segment buffers because we want our water to flow entirely into the shell, and also that it will enhance our heat transfer process and also to get an effective velocity. Okay, as you can see there, the buffer spacing we obtained is 0.22 meter using the calculation from our appendix, which is 1/5 ds, which is 1/5 of our shell diameter. Then number 7, we have the support saddles. Which have the function to support our shell and also to maintain its stability. Okay, then number 8, the exit from our cooling medium, which is called the shell side fluid out. Okay, this is where our hot water will flow out, because at number 4 it will enter as a lower temperature than the oil. So after heat transfer process has occurred, this is where our water will come out. Then number 9, we have our outlet panel, which is the place where our oil, which has been cooled, will flow out from here. Then number 10, we have the separator, so that both the cool and hot oil will not be mixed. And the last one is number 11, is our inlet panel, which is the entrance for our hot oil. Okay, that is all. Thank you. I will pass the presentation to our next presenter.
Next, I will continue this presentation by briefly explain about the calculation. In this calculation, we use the effectiveness NTU method in order to analyze the proposed heat exchanger by setting the inlet volume flow rates of water, which is 20 liters per minute, and the inlet volume flow rates of hot oil, which is 8 liters per minute. We also set the inlet temperature of fluid, which are 20 degrees Celsius for water and 120 degrees Celsius for oil. Therefore, what we have to determine in this calculation is first to find the heat transfer rates and the outlet temperature of fluids. Okay, firstly, we assume the heat exchanger is to be in a steady state operating condition. The heat exchanger is well insulated. The changes in kinetic and potential energy of fluid streams are negligible, and the pipe have a thin wall. First and foremost, we have to find the mass flow rates of fluids. So this is the step where we have to find the fluid properties from the thermal table, which include density and the heat capacity of water and oil at the prescribed temperature. Then from that, we can find the mass flow rates by using the formula shown here. The mass flow rates of water is known to be 0.333 kg per second, and the mass flow rates of oil is 0.11052 kg per second. Next, we can calculate the heat capacity rates of hot oil and water in order to find the minimum heat capacity rates, Cmin, and therefore we can find the maximum heat transfer rates, Qmax, later on. So based on the following calculation, we get to know that the minimum heat capacity rates, Cmin, is 0.255 kilowatt per degree Celsius, where it is determined from hot oil, and the heat capacity rates of water is 1.392 kilowatt per degree Celsius. Therefore, we can compute the Qmax, which is known to be 25.5 kilowatt. Next step is to calculate the heat transfer rates. First, as mentioned before, we have set the type and the size of proposed heat exchanger, right? So from there, we can find the surface area of the tubes of heat exchanger. And by computing this area formula with the total number of tubes is 20 and 0.02 meter inner tube diameter and 2 meter tube length, the surface area is found to be 2.513 meters square. Next, to calculate the overall heat transfer coefficient U, then we need to determine the log mean temperature difference. This is where we use LMTD method by assuming the outlet temperature of water, which is 35 degrees Celsius, and the hot oil, which is 37 degrees Celsius. Then, we shall find the temperature difference between the two fluids at the two ends, inlet and outlet, where delta T1 is found to be 85 degrees Celsius and delta T2 is 17 degrees Celsius. Next, after finding the delta T1 and delta T2, we can compute the log mean temperature difference, delta TLM, by using the following equation, and we get the value which is 45.25 degrees Celsius. After finding the delta TLM, we can calculate the overall heat transfer coefficient, where U is equivalent to Q max over surface area times delta TLM, and we get 0.224 kilowatt over meter squared times degree Celsius. Next, we can determine the NTU from the following formula and get 2.207. And we also have to compute the capacity ratio, C, which is the ratio of C min over C max, and get 0.183. From table 11 for Channel textbook, the value of effectiveness of heat exchanger for one shell pass and two tube pass can be determined from this equation. From that, we get the value of effectiveness, which is 0.833, where it is equivalent to 83.3%. Next, the heat transfer rates Q can be determined from Q equal to effectiveness of heat exchanger times Q max. Therefore, we get Q equivalent to 21.195 kilowatt. Next step, after finding the heat transfer rates Q, we can finally calculate the outlet temperature of the cold, which is water, and the hot fluid, which is hot oil, by using the following equation. And we get the outlet temperature of water is 35.23 degrees Celsius, and the outlet temperature of oil is 36.88 degrees Celsius. Lastly, percent temperature drop that was occurred in this type of heat exchanger is found to be 69.3%. The outlet temperature of water and oil, as mentioned before, is practically identical to the outlet temperature that we assumed before. Therefore, we do not need to re-evaluate the properties. That's all for calculation part.
Okay, I would like to continue with our heat exchanger prototype part. So first is that in this prototype, we are encouraged by Dr. Azlina to use recyclable material. So what I've done here is that I've used, for the shell part or the outer part of the body, I've used a mineral bottle. And then for the tube, the U tube there, to replicate the U shape, I've used a flexible wire case where I could also find in my house. And then for the inlet plenum, outlet plenum, shell side fluid out and fluid in, the white part is actually a tube casing that I could also find in my house, and it can be reused after this prototype. And then for the baffles, separator, and also the tube sheet here, which is quite hard to be seen, it's actually made up of cardboard. And the baffles, I actually try to make like the round shape, but it's kind of complicated because of my bottle is also round shape. So yeah, I hope this replicates the baffles well. Next is the simulation results. So this is for the statistic parts. So for our statistic, we have decided to use the ANOVA methods, and the ANOVA method that we have chosen is one-way analysis, which only require one-way data. So this is our table, or the relationship table that we have used, which volume of cold water inlet, the Q, and the effectiveness of the heat exchanger. These three with 11 variation of 11 different variations. So our I'm sorry that we didn't include our H null and H alternative here, but in our report we do include it. And then for our H null, it is actually mu1 equal to mu2 equal to mu3 until mu11. And for H A, which is H1, is the means are not equal. And our alpha is actually is 0.05, which is 95% confidence. And from this analysis, I have obtained the ANOVA data results. This is the summary. So this is the sum squared, df is the degree of freedom, and ms is the mean square, and f is the frequency. So here, the F that we obtain is 0.13, and the F critical that we obtain from the A alpha equal to 0.05 table, which is 3.21. So our F is actually smaller than our F critical 3.21. Therefore, we fail to reject the null hypothesis, which shows mu1 equal to mu2 equal to mu3 until mu11. And this is our simulation graph. This is for our heat. We have simulate the V cold in volume of cold water inlet versus effectiveness. So as you can see, our volume of cold water inlet increases as the effectiveness increases as our volume of cold water inlet increases. This is due to the relationship of where when the volume of cold increase, we would have increase in Q max, and our effectiveness of go to Q max over Q. Q over Q max. So that's so here I can conclude that the volume of cold water inlet is directly proportional to our effectiveness. Yes, just that. Thank you.
Okay, so I will continue on the last part, which is safety and environmental issues. So heat exchanger operation and maintenance contain potential safety hazards. If such hazards are not treated properly, and unexpected events may occur. Heat exchanger safety hazards could come from improper design, operation, or its maintenance. So in order to prevent this from happening, these following heat exchanger safety precautions can be applied to prevent any accidents. So first, make sure to decide appropriate design condition for the heat exchanger, such as heat exchanger type, temperature design, material compatibility, and structural design. The heat exchanger should be designed for a safe maintenance environment. Second, beware of tube leaking caused by corrosion. If fluid in hot and cold sides mix, a reaction may occur. A corrosion monitoring, inspection, and leak detection are very important. Avoid skin contact with hot fluid that may cause skin burn. Okay, so that's all from us. Thank you.